Alrighty then. Today, let's look at a little bit about higher derivatives. So we've been talking about the first derivative. And of course, the limit definition will never change. And the definition will never not be this. So it's the limit as h approaches 0 of f of x plus h minus f of x over h. Well, you're like, what would the second derivative be? Well, it's exactly what you think it would be, silly goose. It's the rate of change of the rate of change. Aight? So for instance, let's say f of x was your displacement. So like in physics, perhaps you're falling off of a building. Mr. Groom, I'm falling off of a building on the 4.9. Let's make this t, by the way, just because it's a function of time. 4.9 t squared plus, let's say, Groom, I jumped upwards rapidly off the top of a building. Good for you. How fast will I be going at any point in time? That's a great question. Well, that would be f prime of t, my friend. And that would be the rate of change. So if this is displacement, then this would be the change in displacement over the change in time, aka velocity, dog. That'd be negative 9.8 t plus 60. And if you think about this, well, this would be your initial displacement. And this would be your original velocity, because as you know, v, or x equals vt. If you just want to know how far I traveled, at a constant rate of speed, that's what you would have traveled. If I add my initial displacement, this is where I started, this is how far I went, cool, at a constant speed. But I wasn't going at a constant speed because I have this is how far, that looks like hieroglyphics. How far while accelerating. Now, by the way, accelerating at a constant speed, at a constant rate of acceleration. Now you're like, Groom, how do you know that? Well, because I do physics. But we'll talk more about that in just a second. You're going to just hang tight, bruh. We got you. Now, what is this then? Well, this is your initial velocity or original velocity. Well, what's this then? Well, this is the rate of change. This is, I shouldn't say it that way. This is how much your velocity changed in t seconds, right? All this up here is how far you traveled while accelerating in t seconds. This is how far you went in t seconds, right? And then f double prime would be, well, what's the rate of change of this? Well, it's negative 9.8. Wait, that's constant. Correct. Wait, is that always true? Well, if you're always doing constant acceleration, yes, this relationship will always be true. Groom, will it work backwards too? Of course it will. Second semester, we'll go backwards. We'll take this, we'll start with this constant velocity and work our way up backwards. Like, whoa, that's pretty cool, bro. I know. Like, what are we going to do with this? Well, let me show you a few things. A couple things. Number one, f prime of x. When it equals 0, friends, you are going to have a first of all, back to that. We say that the x where this happens, x equals, let me write this way, f prime of c equals 0. Then c, so x equals c, is what we call a critical volume. That's what the East Germans would have said in 1989. It's a volume, critical volume. So here it is. Beautiful. What does it mean? Well, oftentimes, and we've used it this way, Groom, it's a max. I know, this is x equals c, and it's a max. Well, it could just as easily be x equals c here, some kind of a min, yes? Nice. And so we know that because our tangent lines are, wait for it, horizontal, yes? Now, there are a few that aren't max and mins. It's not, I shouldn't say it's rare, but there are a few of them. For instance, this guy. And you're like, but Groom, that looks like This is x cubed. I know. I draw it. I knew that. Well, what would the first derivative be? Well, I don't know. Let's find out. 3x squared. Hey, where does that equal 0? Shut up. It equals 0 at x. I know. But it doesn't look like it's 0. That's because Groom draws a piss poor graph. Let's look at it on Desmos.com. It's my day off, but no, I'm here making videos for you because it's for the children, Mr. Groom. Anyway, do you buy that? That looks like it's 0 right there, yes? Briefly. Notice how it had positive slopes, and then it was basically 0, and then it went up again. Wait a minute. Are you saying that if I graphed this thing right here, I get that? Well, yeah, that's literally what I'm saying. That's positive slope. So this describes the slope of this guy. Yes, this guy has positive slopes. Literally, that's what we're saying. This guy has positive slopes. Literally, that's what we're saying. And then right at 0, at 0 slope. That's what I'm saying to you, sir. Correct. Well, wait a minute, Groom. What if I did y double prime? Well, that would be 6x. I know. Well, what would setting that equal to 0 tell you? That's a good question, huh? So also it equals 0 at 0. Interestingly enough, that's pretty slick because look what happens if you graph that line. You get this guy. So clearly there's 0 here at 0. That obviously means something. And then it was negative over here and positive up here. What this second derivative means, and it's always true, second derivative is always talking about the concavity of the function. So this side of the function is concave down. That is, it opens down. This is concave down. That's one way to write it. There's another that is also concave down, right? That is, the opening is down. This one here is concave up. This one here is also concave up. And so your function will be concave down when f double prime of x is negative. Concave up, f double prime of x positive. Well, what about at 0, Groom? Well, at 0, it is neither concave up nor concave down. We call that an inflection point. Bam. Okay. Now I'm going to pick up a graph here just for fun, and we'll see what it looks like, see what you think of it. X squared, a little sine of x maybe. Oh, that's disgusting. Oh, there we go. That's hot, Groom. That's hot. Nice. Now, I want this one because I'm going to try to kill 2 birds with 1 shotgun shell here. First of all, that's a product rule. You with me? Secondly, there's a metric butt ton of derivative where it's equal to 0. Is that true? Oops. Wait, stop. There's a zillion of them. I don't really want to do all of them. Does that make sense? I don't want to. I think that would be awful to do all of them. Obviously, I also think it would be impossible. But let's go from 0 to 10. From 0 to 10, there's 1, 2, 3 maximums and minimums, yes? So let's go ahead and do those ones just between 0 and 10 because I feel like it. So x squared sine x on the interval 0, 10. That's hot. Let's find max and mins, often referred to as local maxes or quote-unquote relative maxes and mins. Relative meaning, Groom, you're the tallest person in the world. No, I might be the tallest person in a stats class or calculus class today. I'm not the tallest person in the world, not by a darn sight. Whoa, Mr. Norton is really smart. He's the smartest person in the world. No, he might be the smartest person in high school. Right there with Ford. Certainly smarter than me, but not the smartest person in the world. All right, that's a relative or a local. By the way, if you taught preschool, you could be 5 feet tall. And you'd be like, "Whoa, wait a minute. I'm really tall. I'm the tallest person." Well, you're the tallest person in a room full of preschoolers. Yes. That's a local or a relative maximum. You with me? Same with the mins. Okay, whatever. Obviously, if you had just a function x squared, it has a absolute or a global minimum, right? Because it only goes down so far, and that's as far as it ever goes down, okay? This one doesn't have any. It keeps fluctuating forever. But irregardless, let's do the derivative. So the derivative of x squared is 2x times the second function plus the first times the derivative of the second function. Hey, that's hot. Oh, I know. Groom, can we put this equal to 0? Oh, well, probably. And so if you do that, there's an x in common, yes? Let's take it out. So 2 sine x plus x cosine x equals 0. True dat, homie? True dat, Groom. True dat. And so if you look at that, you're like, oh, interesting. Interesting. So we have what? Well, x equals 0, I suppose. If you look at the graph, does that match up? By God, it does. How about that? Right there at 0, we had a 0 slope momentarily. And then 2 sine x plus x cosine x equals 0. How do you solve that? Well, you don't, but we can graph. I'm going to go ahead and graph that. Just, oops, come back here, you hippie. I'm going to turn him off. And I'm going to go 2 sine x plus x cos x. There you go. And so you have zeros at 2.28, at 5.08, and 9.72. 2.88, 5.08, 9.72. Okay, 9.72. These are where f prime of x equals 0. These are maxes or mins. Well, which is it, Groom? It's a good question, isn't it now? So let's come back over here and look at this guy for a minute. Okay, interesting. So this is slopes. So the slopes were, now hold on. Let's go back to this piece here, because remember we have to do the entire derivative. There's our entire derivative, yes? Now, does it still have slopes, zeros at the same place? It sure does, but it's imperative when you look at the entire graph. Look at 0. At 0, we had positive slopes on the left-hand side of 0. We had positive slopes on the right-hand side of 0. What that means from a graph standpoint, I had positive slopes, that is, it was coming up. I have positive slopes after, so it's still going up. It must have just been one of these numbers at 0. Does it have to go through 0? No, friend, it could have come up here. It could have been anywhere, but it was coming up. It stopped coming up momentarily, and then took off again. This is you, if you've been lifting weights. Parker's been busting out the big irons, trying to impress the ladies. Nice. Or lady, as the case may be. And so he made a plateau a while back. He was pumping the big irons. He got up to 200 pounds on bench. Attaboy. And he stayed there for like a day. And then all of a sudden, he took off again. Nice work, bud. So that's what that situation would look like, because, again, it was positive slopes, stopped, and then positive slopes again. If you look at this guy here, wherever that was, stop it, go away, you hippie. This guy here, 2.28. Notice that we had positive slopes up here. Are you with me? It was above the x-axis. Down here, they're negative slopes. Yes, right? And when I say they're negative slopes, because this graph I'm looking at is the graph of the derivative. So they're positive slopes, then there were negative slopes. Wait a minute. If it was going up, and then it stopped going up, started coming down, what does that tell you? This must have been a maximum. Groom, can I kind of assume the next one is negative, or is a minimum? Well, probably. We were going down, and then we were going up. Oh, geez, how about that? We were going down, and now we're going up. This is a minimum. And then we were, where's 10? Right there. So on this one here, at this 8 one, we were positive, we're going up, and now we're coming down again. So we were going up, and then we're coming down again. Now, Groom, can I say anything about the steepness of the graph here? Yes, you sure can. Because after this guy here, this 5 one, we were going up like a bat out of heck. So does that mean that we're going to go up higher? Whoa, probably. Yeah, sure. All right, so you could argue that you should have drawn it a little more like that. We're just doing sketches, dog. So this was the 9.72. This was the 5.08. This is the 2.88. Nice. And this is the 0 one, yes? Piece of cake. Piece of cake. Does that look right according to our real graph? Yeah, how about that? We had maximums here at minimums. Maximums, yes? Yay. Okay, so. Did I say 8.09? Why in my mind did I say 9.08? I don't know what I was thinking. Oh. Wait, what did I say it was? It was 8.09. Where did I get my 9.8 from? I don't know. Fix that on your notes, for God's sakes. 8 point something, 8.09. Whatever it is, 8.09. That one. There you go. Fix that, please. Mr. Grimm's having an aneurysm or something. Don't worry about me. All right, so then your first derivative we said was x times 2. No, I could leave it the way I had it, so I'm just going to actually leave it the way I had it. So it's 2x sine x plus x squared cosine x. All right, let's do the derivative of this. But Groom, that will be 2 separate product rules. I know. I'm excited for it. How about you? So it's going to be 2 sine x plus 2x cosine x plus 2x, because now we're on this one now, cosine x. And then take so x squared times the derivative of cosine is going to be minus sine x. And so if you do the math, you get 2 sine x plus 4x cosine x minus x squared sine x. So that baby equal to 0. Okay, now, again, I'm going to hide this so you don't look at it. So it's going to be, what did I say it was? 2 sine x. Why didn't you tell me it was cosine? People don't like me very much. I'll probably get over it. And then, what was the last one, bro? Minus x squared sine x. Bam! So obviously at 0, we had a 0. At 1.5, at 3.9, and at 6.83. So 1.50, 1.51, 3.99, 6.83. This is where f double prime of x equals 0. These are our inflection points. I'm going to say they're my inflection points. Or maybe sometimes something a little different. Okay, so if you look at the original graph, you get this. Okay? Clearly at 0, it changes from being, look at your blue line. Look at your blue one only. It was concave down over here. True that, true that. And now it's concave up. So yes, clearly an inflection point at where? We said at 0. Nice. Now, let's see what the first one was. 1.51. X equals. Okay. Groom's going to change the graph just a little bit. Okay, if you don't mind. Well, I don't care if you mind. It doesn't matter to me. I'm going to do it anyway. X equals 3.99. And x equals 6.83. Oh, shoot. Not 683, you jackass. Okay, there it is. Perfect. Now, if you look at it, right there, you can see where it changes from being concave up to being concave down on the other side of it. Yes? Woo. And it's concave down until you get over to here. This is all concave down until right here. And then it's all concave up, you see, until you get to right there. And then it's concave down again. That's all we're saying. Those are inflection points. Now, what I do want you to pay attention to is this. This is kind of exciting. Where is it going uphill the fastest between 0 and here? It's actually at this critical value, at that inflection point. And so what we're going to see is this. These are inflection points. Yes, true that. But something I never learned as a child, and I always like to pass along to kids now, something I learned later in life, is that at inflection points, this is the steepest, or if you prefer, fastest rate of change on that interval. That is where it's going the fastest. Now you're like, Groom, give us an example. Oh, I'd love to, sir. Love to, madam. So when I say minimum in your life, like, I'm so sad. This is the worst it'll ever be, bud. I'm going to start coming back uphill. When you start coming back up out of your funk, how did you feel today? Well, I didn't cry all day today. It was only like 7 hours. That's an improvement. Oh, how was your day today? It was pretty good. I only cried one time. Okay. How was your day today, Mr. Groom? I had a great day for the most part, but I didn't tear up at all. Oh, that's awesome. Mr. Groom, I'm the happiest I've ever been in my. I'm doing really good. I'm doing really good. Oh, that's amazing. And then tell me these stories, and you're like, Mr. Groom, how is it today versus yesterday? It's still better than yesterday. How is it? Well, it's pretty good. It's actually good, and so forth. And what you'll notice is that some people have this idea that, like, I'm pulling out of the funk, and I start out of the funk. Notice as I come out of the funk, the rate of change here, it's positive, but it's not real positive yet. And all of a sudden, whoa, the most positive ever. And then what happens? Well, then someone comes and poops in your cereal again, and then it starts to kind of, and then, this is the maximum it's ever been. It's still going up. This is the best it's ever been. We're not going up any higher than that. And so, but right there, this was the best, fastest rate of going up that it ever was. And we call that an inflection point. Okay. Looking back is usually when you notice these things. You don't normally notice them from a philosophical standpoint or just a history standpoint a lot of times. Looking back, you're like, that was the high water. That was a situation where, boy, things were going great, and then they stopped getting better all the time, like rapidly getting better. They were still getting better, but they weren't getting any better as fast anymore. And then we reached a kind of a tipping point where, like, okay, over the top we come again. Okay, economics talks about those as well, oftentimes. Anyway, and then back down again and whatever. Yes, and up and up and up. There we go. Again, your inflection point right there, where it changes from being concave down to being concave up, that will always be the steepest rate of change. Okay, always. Okay? So, good times, pretty easy to do, not terrible. The ones I will give you on the homework, some of them I'm going to do some nice easy ones, like this fella, f of x equals... pause while I find an easy one, because I want this to work nicely. Pause. Okay, there's this cat, for instance. If that was your original function, then f prime of x. Oh, and by the way, a cubic looks like this, yes? Possible it has a max and a min? Possible. Possible that it just does one of these numbers. It doesn't really have a max or a min. That's also true, right? So when I do this, that's going to be x squared plus 4x plus 4. Hey, set that equal to 0. Hey, that's hot, Groom. Damn it. Oh, pause. Don't write that down. Pause. Well, go ahead and write that down, but I'm just going to make this a 3x instead. I want this to be different. Oh, shoot. Dumbass. Okay, now, set equals 0. There you go. I wanted this to work out a different way. You with me? Sorry about that. Set that equal to 0. Factor it. X plus 3. X plus 1. What does that mean? Well, it means that at x equals -1 and at -3 we have relative, well, first of all, we have critical values. Probably max, probably min, because Groom, I've seen this. I've seen this story before, Groom. Cubic function looks like this. It starts down and finishes up. Lo and behold, I bet that's a max, and I bet that's a min. I bet you're right. But if I didn't know that, I'm going to put in a number. That's a max. This is a min. Mr. Groom got lost in the number line for a minute. I'm sorry. Now, let's pick a number that's over here somewhere. Again, here's -3. Let's go -5, for instance. Why? Because it's less than -3, bruh. So if you put -5 into this fella, what do you get? You get -5 plus 3 is -2. -5 plus 1 is negative. Negative times a negative is a what? A positive. Is a positive. Yes. Is a positive. Mr. Groom, can you try to do what you're supposed to do? So what I said was my original function must look something like this. Yes, that's what I'm saying. But when I look at this graph here, this is a parabola. Yes, and I know it has a 0 there and a 0 here, right? Wait a minute. Yes, true. So when I put in -5, what do I get? -5 gives me a positive slope. What if I put in a number between -3 and -1? You mean like -2? Sure. Put -2 in here, I get 1 times -1 is negative slope. Negative slopes. So between here and here, I'm having negative slopes. Yes, that's saying. That's why it's under the x-axis, obviously. The slope here is 0. We already talked about that, bro. Pay attention. Now, if you pick a number out here, you mean like 0? Sure. If you put 0 in here, you're going to get 3 times 1 is 3. It's a positive slopes out here. Positive slopes. Meaning that, listen, if I had positive slopes and then negative slopes, it was going up and then it turned and came back down. At x equal -3, we had a maximum. And then we had negative slopes and then positive slopes. That means x equals -1 is a what? The minimum. Now, how many inflection points do you see here? If you're just doing the math at home, you're like, whoa, Groom, I only see one inflection point. And I bet it's going to be somewhere between -3 and -1. Well, I bet you're right, sir. So let's start off with this fella. And let's take the derivative of him. That's 2x plus 4. Set it equal to 0, you get x equals -2. At x equals -2, we had an inflection point. That's true. And what did that tell us? It's also the fastest it's going to be going up. So it's going to be 1/3 x cubed plus 2x squared plus 3x plus 6. Hey, look, dude, I see a maximum here at -3. I see a minimum at -1, yes? And then if I put in -2, well, x equals -2. X equals -2. What is just happening? What in the devil is happening? That is the spot where it's coming down the steepest. But it doesn't look that steep. No, you're right. It doesn't really look that steep. It doesn't look that steep, but that is the steepest that it's ever going to be, is between, in that value, it's going to be at -2. Notice it was concave down on this side, concave down, yes, all the way to there, and then concave up from here to all the way to there, yeah, concave up. That's the game. I know what you're thinking. Can you do higher derivatives than the second derivative? Yeah. You want to do another one? Sure. F double prime of this cat, or triple prime rather, is equal to 2. Done. That is, at that point, that's as far as this one will go. F, and normally write like this because you run out of room up there for 14 of them. It's 0. It doesn't change after that. Does that make sense? This was constant change. This is no change. For some things like sine and cosine, it'll just be sine, cosine, negative sine, negative cosine back to the top, right? Some of those will go on forever because they're literally always changing. That's what periodic functions do. They just always change, okay? What I always tell kids, first day I teach periodic functions in Algebra 2 or pre-calculus, what's the first thing that comes to your mind when you hear the word period? And you always pick on a kid who's going to kind of turn beet red, which really makes it laugh. Then you're like, well, the dot at the end of the sentence, you liar. No, it's called periodic for a reason. They constantly are changing. That's what they do. Okay, they're periodic functions that constantly change, and after a certain period of time, they change again. How fast they change? Well, the first derivative talks about how fast they change, and the derivative of the derivative talks about how fast the derivative is changing, but it talks about how fast the first one is accelerating, if you will, right? And then what is the third derivative? Well, it's the change of the acceleration. Okay, in physics we call that jerk, but after that there really doesn't mean anything, but it's still just, it's a rate of change of the previous rate of change. That's all it is. And so it's kind of a neat thing. The only place that really going to show up, you're going to see this a little bit later on, we're actually going to be creating functions, creating polynomials that will mimic a bigger, nastier function. So like, I don't know, ln times the x squared times the sine of x times the something else. And you're like, that's a disgusting function. Wouldn't it be cool if we could create a polynomial that looks just like it? And turns out we can. And part of doing that will be taking a bunch of derivatives. Okay, in essence, it would be like if I wanted to mimic someone, I'd have to like dress the same as them. I'd have to talk the same as them. And the more I go changing myself to be like them, to match them, the more we're going to look and act or whatever alike. We'll be more recognizable together, if that makes sense. And so that's something that we will do later on with multiple derivatives. Okay. So, but again, once you get past the second derivative, we don't do a ton of that. All right. Thank you.